Okay, so let's run through some of the basic properties of alkanes. We'll see this throughout the next few chapters. Anytime we get a hold of a new group of molecules like the alkanes, basically what we'll do is we'll talk about the physical and chemical properties of this particular group, like the alkanes. And physical, we mean stuff like this. We're talking about what distinguishes gases versus our liquids. Just sort of basic things like that. Small molecular weight compounds are typically gases. And you see that, let's say, for the first four hydrocarbons. And this is butane, and just let me take a moment to sort of dissect the bond line form for a minute. Remember, we got a zigzag, each endpoint, each bend, or if you had a branching point, each intersection represents a carbon, and then there's a certain number of hydrogens. For example, there's 2 hydrogens coming out from this carbon to complete the valency, and since one bond is shown here, there are 3 hydrogens coming out on this compound. So it's a C4 H10, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. The intermolecular forces are just not that great. So therefore, at room temperature, there's enough energy to get these dispersed as a gas. You get up into gasoline, basically, right? Octane content in a gasoline. It's a mixture of these, or probably heptane, octane isomers, somewhere in that range for your gasoline mixture. And again, the molecular weight increases, the degree of intermolecular forces increase, etc. If you get beyond 8 or so, these are higher boiling point liquids. Okay, like kerosene, mineral oil. So there's they're making a distinction. Each time you go up a little bit more, it gets a little thicker, a little less volatile, and then at some point it gets gooey, if you will. These waxy solids. Think Vaseline. And as it turns out, why do apples shine and I guess retain water as well as they do? Well, there's like a high molecular weight alkanes and some waxes on the surface of the apple and a lot of other plants that help retain the moisture content for the plant, or in this case the apple. And you also see this trend in terms of increasing molecular weight, and what you're looking at. Just looking at crude oil, crude oil is basically it's a very complex mixture of hydrocarbons, and alkanes are part of that story, if you will. In this little diagram, I don't know how well you can read the individuals on here on the video, but there's you take the raw crude oil here, you heat it up, and you do distillation or a fractional distillation in these refineries. And what comes out up top at I guess lowest temperature, right? This down here is closest to the heat source, so higher temperature to lower temperature. And what can happen here is that the gases make it out the top, and you get this fractionating of the crude oil mixture from gasoline, kerosene, and then down here asphalt and tar. Much higher molecular weight hydrocarbons. Again, it's not all alkanes, but it's sort of consistent with what we've said in just the past few slides about the physical state based on molecular weight for the alkanes. And this is just a little bit more quantitating, if you will, that diagram earlier. So physical state, fine for alkanes. There's also another aspect of physical properties, at least the top part here anyway. We're going to say physical properties, and it's right here, flammability. Air. That's a chemical property, and that's really the only chemical property that we talk about for alkanes. But first off, let's cover these physical properties. And why is there a picture of an oil slick here? Well, really, what this is doing is it's illustrating all these physical properties. Crude oil is it's a hydrocarbon. Alkane is a hydrocarbon, and what happens to most crude oil? Floats on top of the water. What that is showing us is the fact that it's floating on top of the water is that it's less dense than water. There are some fractions of crude oil that's a little bit denser than what you see here, and they'll settle, below the surface of water. But you saw your classic picture of a oil slick. You see it floating on top, and then they'll wrap this around with buoys trying to keep the oil slick contained. And again, they're taking advantage of the property of the density property of the crude oil, and it's also insoluble in water. One thing that we learned is that anything that's just a plain old hydrocarbon is going to be nonpolar, and something like water is polar. And the two substances just don't mix, which is good for the purposes of trying to clean up this mess here. You have a much better chance of getting that crude oil out. And this is, again, what we're seeing in this particular section. It sets the stage for all the upcoming functional groups that we talk about in terms of their chemical and physical properties. And we'll run through solubility in water and the density with respect to water. Solubility in water becomes more important as we move into the other functional groups. But again, this is sort of setting the stage in terms of what we talk about when we talk about organic compounds. And getting to the last topic, the flammability in air, this is a combustion reaction. So here's a typical combustion reaction. This is a balanced equation. I'll go through one in just a second. But basically, these the carbon and carbon-hydrogen bonds, they contain energy, what we have here. And when you ignite it with the proper ratio of oxygen, let's say in this case a 1 to 2 molar ratio between the two reactants, you get the complete combustion of the methane molecule, and a lot of energy being kicked off, right? Thermal energy, kinetic energy associated with the particles, etc. But usually we think about it as heat, thermal energy. So what do you need to do with this? Well, know the basic concept, what I just mentioned here, but also examples like this. Balancing a combustion reaction. So you can look at this one and walk through, 3 and 4 are needed and 5 are needed here, etc. I actually want to do one because I think that's really the best way to learn this, obviously. And the way let's say the problem is going to be set up for the test would be something like this. I would give you a hydrocarbon, and this isn't an this is a cyclic alkane is what we're talking about here, but anything that has a high carbon-hydrogen content is going to burn. And so I will give you the molecular formula. I might tell you, okay, it's a liquid at room temperature, and then you would need to complete the rest of the equation. Right? So that means that you need to know that in a combustion reaction that we're talking about here, it's reacting only with oxygen gas, and oxygen is a diatomic molecule. And the only two products that we're going to get are water and L or G, it doesn't matter. And the heat that typical combustion reactions taking place, this is coming off as a gas, so I don't get too worried about that. But CO2 is definitely going to be a gas there. So we have our subscripts, we have our two products that are formed in these compounds, and then what we need to do is then go back and balance the equation. So that's the second part that you need to be familiar with. Now, there's a particular hint or rule, if you will, for balancing equations is this issue here. If you see an element like oxygen, oxygen is in both of these products here. When you see an element in that state spread out over multiple compounds on one side of the arrow, do that last. And so usually when I set up a combustion reaction, especially for the purposes of teaching how to do it, I set it up like this. Start with carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. Just sort of your typical layout of the combustion reaction sort of gives you a hint about how to balance the thing out. And what I see is that we have 5 carbons, right, 10 hydrogens and the 2 oxygens. Oxygen count isn't necessarily that important right now because by the time you get down to this last one here, all the oxygen numbers get rearranged anyway. So anyway, sometimes I just leave oxygen out until the very last. Oh, and then 1 carbon from the carbon dioxide, and then we have 2 hydrogen atoms. So let's balance the thing. And what is our goal here? Well, we want to adjust these coefficients in front so that, right, conservation of mass is met. That little law of science that we see over and over again and every time we balance an equation. And, the question is, and again, this is, for teaching purposes, what number times 1 equals 5? Well, that's 5. Well, the reason why I sort of poke at it like this is the idea that, the coefficient that you're putting in front of the molecule, remember, that's what you're multiplying all the way through here. So I'm not going to do the oxygens yet, but notice that I've dramatically increased the number of oxygens by adding the 5 here. But I'm going to adjust the oxygen count at the last because look at this next step. Basically, why did I focus on 5 here? It's because I had 5 there. Now I have 10, and I need to get this up to 10 as well. Okay, well, for this particular example, that just happens to be 5 as well. So, all right, 2 times 5 is 10, and that multiplier is the value that is placed in the molar coefficient for the hydrogen or for the water molecule. And again, notice, and I just really want to mark that out. Why do you save oxygen for last? Why do we have that little hint in chemistry about if an element shows up in multiple molecules on one side of the arrow, whether it's product side or reactant side, but in this case product side, then we save it for last, because as we tweak the number here and as tweak the number here, then oxygen gets changed in each tweak. So why worry about oxygen from the beginning? You do it to last. Now you have at least hydrogen-carbon balance, and you can go back and take an inventory. And let's just keep that in blue just to sort of give us a bit different picture. 2 times 5, that's going to be 10 oxygen atoms from the 5 carbon dioxide molecules. 1 times 5, that's 5 there. So we actually have 15 oxygen atoms on the product side now. Okay, same kind of logic. What did I do here? I said, my original count times some number equals what I need. Well, for this example, if we apply that same logic here, think about that. What should be in that box? What's the easiest thing that I can put in that box so that 2 times that number equals 15? Well, the easiest thing, notice, I can put a fraction in there if I need to. And this works for the balancing act. Again, same kind of logic. I need to multiply this count of oxygen on the reactant side so that it's going to match up with what I know I need on the oxygens from the product side. So 15 halves. So what does that look like? It looks like that if I put it up here in the balanced equation. And if I went in and I, checked the numbers and everything, sure, it would be balanced, but we don't, well, I'm going to say this, don't leave the fraction. Instead, we want to do one other little trick, and you may have seen this in the Gen Chem class. We want to multiply all the way through by 2 so that we can get rid of that 2, that fraction there. And in the process, let me just sort of rewrite the whole thing down here. Final answer. It's a liquid. Alright, so 1 times 2 is 2. 2 times 15 halves is 15. That's a gas. And now 2 times 5 is 10. H2O. Liquid or gas, it doesn't matter. And then, oh yeah, same thing here. So 10 carbon dioxides as well, and that's definitely a gas. And that's our final balance equation. So again, whenever you get an odd number down here with oxygen, think about this little trick. It's okay to use a fraction to get through the equation like this. But again, this down here would be the final answer that you would need to give me for the test. And remember, the only thing I'm going to give you is the molecular formula, and I'm going to ask you to complete and balance the combustion reaction. So all of this stuff you would need to provide to me to get full credit for the problem. And that's enough. And again, this is the only type of chemical reaction that alkanes are involved in. Okay, thanks.